Alright, thanks for watching. And you might wonder what a PDE is. I'm sure you've heard of those letters, PDE, and you're probably like, what do they mean? Well, this video is for you. So a PDE, what it is, it's what's called a partial differential equation. So you may or may not have heard of differential equations, maybe in physics classes or maybe in calculus classes. But just to give you a little overview, differential equation or ordinary differential equation is an equation which relates a function with one or more of its derivatives. So for instance, a very typical ODE is y double prime plus 4y equals 0. Again, an equation which relates a function y with one or more of its derivatives. Well, a PDE is just a higher dimensional analog of this. Because here we're really taking the derivative in one direction, but in PDEs we can take derivatives with the x direction, with the y direction, really any direction that you want. So a partial differential, again what it is, it's an equation that relates a function, just like here, with one or more of its partial derivatives, which are the x derivatives and the y derivatives. For instance, consider this function, u equals to u of xy. So it's a function of two variables, the x variable and the y variable. And then a very typical PDE is the following one, uxx plus uyy equals 0. And this is called Laplace's equation. Which is very cool, because in French, Laplace means the place, so you know you're in the right place when you watch this video. But what does that say? It says, suppose you have a function u, and you want to find all the functions with the following property. If you take two derivatives in the x direction, and you add two derivatives in the y direction, it should give you 0. And indeed, you might say, hey, that sounds like an equilibrium situation, and indeed that's what Laplace's equation measures. It's just some fluid that's in equilibrium. And you might say, hey, I learned so much about ODEs, why in the world should I bother with PDEs? Well, let me ask you this. Are you an ant living in one dimension, or are you an anteater living in higher dimensions? Shout out to UC Irvine. Well, just like, multi-dimensions is important, PDEs are probably more important than ODEs. And in fact, there's one thing I love that my PhD advisor, Craig Evans, said, if you can solve all PDEs, then you completely understand the universe. Which means two things though. On the one hand, PDEs are extremely powerful. Every PDE is its own little universe. And if you solve them, you just have a complete overview of the universe. On the other hand, PDEs are freaking hard because it turns out the universe is kind of hard to understand. On the other hand, the good news, as I said, is that actually many physical phenomena can be studied with PDEs. And in fact, let me tell you a couple of reasons why you want to study PDEs. First of all, they arise in physical sciences. So in physics, in chemistry, whatever. So for instance, there's something called Schrödinger's equation, which arises in quantum mechanics. And I think it's supposed to be the mother of all quantum mechanics. So it's very important. Euler's equation, and then has the name Euler in it, so it's probably important. The Maxwell equation for light. I don't know if you've seen this shirt. You have this complicated equation, and then there was light. Well, that's actually Maxwell's equation, which is a very complicated PDE. And then, of course, Einstein's equation in relativity, again, the whole foundation of relativity are based on some PDEs. And also, there's something called Navier-Stokes equations to predict the weather. And I'm sure everyone's interested in it because it turns out if you solve the Navier-Stokes equations, you win $1 million. Yeah, it's one of those $1 million prizes, so millennial problems. So definitely check it out. I tried it way too hard, but maybe you can do it. I believe in you. So one thing, physical sciences, and also, just a little blurb, my PhD was a PDE in chemistry, so they also are raising chemistry. And I invite you to watch my 100th video special if you want to find out more about this. So physics, also, if you like more math, geometry. I don't know if you know, but there was this open conjecture for a long time called the Poincaré conjecture. And it's been open for 200 plus years. But it's been solved by Peyam fairly recently, and he used the Ricci flow and area minimizing surfaces to solve this problem, which is another kind of PDE. And then, don't like geometry? Well, there's another math subject that's cool. Probability. There's actually something called a stochastic PDE, which is kind of a random version of a PDE. And, well, it is a partial differential equation. So it works, and also turns out sometimes from completely chaotic processes, you can sort of extract a very deterministic PDE, which again is a PDE. And also Brownian motion can be simulated with PDE. And also if you want like airplane simulations, that also uses a PDE. So very useful in life. And the next contestant, optimization theory. Because it turns out when you maximize or minimize a function, bam, something called a Hamilton-Jacobi equation appears. And that's also a PDE. So very important, very hard though. And then image processing. Well, whenever you have an MRI, hopefully not, well, it's based on this technology is based on PDEs. And in particular, if you want to figure out, for example, how to get an even better image of your MRI, I think it's called an inverse problem in PDEs. And it's also very, very useful. So image processing. And lastly, one thing that I'm sure everyone wants that I don't have, which is money. I forgot. I didn't bring my wallet, but imagine like this is money. I'm like, woo! I'm throwing dollar bills. Just like Beyonce said, bills, bills, bills. Anyway, money. So it turns out in finance, PDEs are also used, and those are used in there's something called the Black-Scholes equation, which is another PDE in finance. So again, as you can see, each PDE it's its own universe, and solving a PDE amounts to explaining the universe. And not only that, because since we're like at the subject of what a PDE is, well, let me give you some examples of very prominent ones. So it's sort of the Hall of Fame of PDEs. And sorry if the one you're studying is not on there. There's so many of them because they're so useful. First of all, one of the simplest PDEs, not the simplest PDE, but one of them, suppose u is a function of space and time. So x is space and t is time. Then there's something called the transport equation, ut plus 3ux equals 0. And again, it's called the transport equation because it measures how the density of a function changes as it gets transported. And in fact, the solutions kind of look of this form. You start with some profile u, and then after some time, the profile just gets shifted, if you want, by 3 units. So how cool is that? So it is a transport equation. Then there's something called ut equals uxx. And is it getting hot in here? Well, yeah, because this is the heat equation. And it measures the, how the fluid sort of evolves as it, like the temperature, if you want, of a fluid over space x and time. So suppose you have some rod here of either finite or infinite length and some time t, then uxt, what it does, it gives you the temperature of that rod at position x and time t. So you see, you have many variables in play. That's why partial differential equations are more useful than ordinary ones. And I was so obsessed with ODEs, but once I studied PDEs, I was like, wow, no, this is much better. So definitely try it out. And then something really interesting. So here we have ut equals uxx. You may ask, what if we add an extra t? Shouldn't change anything, right? I mean, it's just an extra t. Like, how bad can it be? Well, just like an extra chromosome, it's pretty bad. Because it turns out this equation is very different from this equation. This is called the heat equation. It has nice properties. Things become smooth. Things decay to 0. This is very bad. This is the wave equation, and what happens, solutions with corners still have corners everywhere. So, and that said, it's still a very useful equation. It measures, if you want, the height of a wave. Like suppose you have a wave here at position x and time t, uxt gives you the height of that wave. That's one thing, again, very different from the heat equation. And then you have the equation I already talked about, uxx plus uyy equals 0, where u is a function of 2 variables. That's what's called Laplace's equation. And what it does, it measures the, if you want, the temperature of some metal plate, but after a long time. So think like ut equals uxx plus uyy, but u becomes constant in time and this becomes 0. And generally anything in equilibrium can be studied with Laplace's equation. So the examples 2, 3, and 4, they're very important ones. In fact, the ones that are studied a lot in an Intro to PDE course. But you could have fancier ones, why not? Example 5. What if you add an inhomogeneous term? Because there's no reason why the right-hand side should be 0. It could be also f of x comma y. And that's what's called Poisson's equation. Which, by the way, YouTube doesn't like. Every time I put Poisson's equation, it reports me or something, because it sounds like another word with just one S, and that's a bad word. Anyway, so this is Poisson's equation, also very useful. And the one maybe I talked about also, whenever you have a max or a min, it's called Hamilton-Jacobi equation. So if u is again a function of position and time, and h is what's called a Hamiltonian, then you have ut plus h of uxx equals 0. And that's an example of actually a nonlinear PDE, because it's not linear in ux because of this weird term that could be squares. A nonlinear PDE, but it's actually well studied, that we actually know lots of things about. So that's good. And then there's something related. I like the name of this equation. U plus u, ut plus ux equals 0. That's called Burger's equation. So not like hamburgers, but this guy burgers. And it's very useful because it's a great model for traffic flow. And in fact, this is one of the PDEs that actually has shocks. I know, shocking. Because what happens, it turns out this PDE, the solutions, are maybe constant on this line and constant on this line. But the question is, what happens here when the lines collide? And then, you have to define what's called a weak solution or a generalized solution to see really how to continue that. And I guess just so the solution to the problem is you basically follow the path that has the least energy. So that's cool. And then you have that, and then you have, surprisingly, those are the easiest kinds of PDEs to study. You can also have those kind of PDEs like a very, very good example for a very complicated PDE, which is uxx, uyy minus uxy squared equals f of xy. Or in generally, determinant of the Hessian equals f. That is the Monge-Ampère equation, and one of the hardest PDE to study. In fact, it's so hard. First of all, Cédric Villani won the Fields Medal because of that. And also, it's so hard that a whole math subject was invented because of it. The whole theory of optimal transport exists to solve this PDE. So again, you can see how useful it is. A whole math subject is invented because of this. How crazy is that? And then notice, even though it's hard, it's only second order, you could also have more complicated ones. Well, how about third order ones? ut plus ux, like Burger's equation, plus uxxx equals 0. It's called the Korteweg-de Vries equation, KdV equation. And again, those are examples of PDEs that are higher order, but that are supposedly understood. You could even go like 27th order KdV equations and you can still solve them. I believe you solve them with what's called solitons. So not solutions, but solitons. And I actually went to a really cool talk. It's just so long ago, I don't remember, but I do remember it was cool, where the speaker used Galois theory to solve those equations. I was like, what? Oh. Good for Galois, I guess. Or anyone who likes algebra, but luckily you don't have to know algebra to study PDEs. It's a good safe haven. And then another one, again, as I said, the basis of quantum mechanics, ut equals I uxx. I hope it's either I or plus I know that, so I know that. So that's Schrödinger's equation, very useful for quantum mechanics. And lastly, the PDE I care most about, because it's the PDE that got me the PhD. ut equals to sigma over tau, u xi, xi. And again, PDE, that's using chemistry. And lastly, after those examples, let me just give you a little blurb on how to study PDEs. So there's actually a whole bunch of math subjects that are just related to studying PDEs. One is finding exact answers. And the thing is, in undergrad, you're so used to finding exact answers of ODEs, sadly not true for PDEs. Soon you'll see you'll give up. I know I was like, no, I will find all the answers. No. I promise you will not find all the answers. But it's okay. Just like for integrals, not all integrals have a name. Not all PDE solutions have a name. And it's okay. You'll get used to it. And there's also something called series solutions, which, again, the foundation of Fourier series was to use to solve the heat equation. That's why Fourier invented his own series. And then, after a while, you can be like, okay, I sell my soul and I just study them numerically. So how can you study PDEs on a computer? And I'm only half kidding with the selling your soul, because it's actually very important, especially in applications, right? To study them numerically and get accurate pictures. And there's also something called asymptotic methods, which are, it's a very cool branch of math, which just says, well, suppose you have a PDE and you change your solution a little bit. What PDE does that solve? Or similarly, can I solve a more complicated PDE as a limit of easier ones? So that's really interesting. I taught a course on that, so I remember it being interesting. I don't remember that course anymore, but it's cool. And then lastly, one very, of course, for me at least, very useful subject, theory of PDEs. Namely, how can we study properties of solutions without even finding them? Like, without solving the equation, how do we know it has a unique solution? And there are a bunch of methods for that, like energy methods, maximum principle methods, and whatsoever. All right, I hope you like this little intro to PDEs. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.